Thank you very much, Steve, for the opportunity to talk here and present the work of my PhD. I'm going to be talking about fast ice thickness, mainly about interannual variability in that, and then also about measuring ocean conductivity in supercooled water. I'm based at the University of Otago in Dunedin, New Zealand, supervised by Inga Smith, Greg Leonard, Pat Langhorne, and Pete Russell. And this work is also done in collaboration with Andy Marnie, Matthew Parry, Kate Turner, Brittany Schmidt, Lars Smedsrud, and Dan Ditchek. My PhD is funded by the University of Otago, Antarctica, New Zealand, NIWA, and part of the work that I've done for this presentation is also funded by the Royal Society of New Zealand Marsden Fund. Steve has asked me to do a bit more of an introduction about who I am and then also introduce all of these topics a bit more, seeing he has invited some of his graduate students, and I'm excited to have this opportunity to talk to a wider audience. So the talk will be in 4 parts. It's more or less an outline of who I am, what is sea ice and supercooling and why does it matter, measuring supercooling, and then drivers of interannual variability in fast ice thickness. So I'm originally from Germany and did a year abroad in Canada. After finishing high school, I started a bachelor's degree in physics of the Earth system, specializing in oceanography at the University of Kiel and at the Geomar-Helmholtz Institute in Kiel, which is in northern Germany. Did a short stint at the National Oceanography Center in Southampton, and then started my master's at the University of Bremen in collaboration with the Alfred Wegener Institute in Bremerhaven, where I worked on glaciology and on physical oceanography. During that time, I took a year and did a postgraduate diploma at the University of Otago in marine science, and then came back here in 2018 to start my work towards a PhD at the University of Otago. Some of the perks of doing polar research is that you get to see nice animals that I do not actually study, but my grandmother still thinks that I do something to do with whales. So I have a whale here, the polar bear, a walrus, and this is off the coast of Greenland, where we were with RV Polarstern, which is the German research icebreaker, traveling from Svalbard to Greenland. I was mainly in charge of physical oceanography and sea ice remote sensing for navigational purposes. So I did a lot of scrubbing of buoys, very little sitting in the sun because it was only sunny for one day. It was quite foggy. We recovered a lot of moorings along the way and deployed new ones. And some people on board also did meteorology and biology from that ship. After I switched poles, I got to travel to the Antarctic twice, and you can see here the approach to the continent from the C-17 and then landing on the ice. We worked out of Scott Base, and you often have Mount Erebus, this big volcano in the background. This is me towing an EM31 instrument, which measures sea ice thickness continuously as you tow it. I again did physical oceanography out of container camps here, which you can see down here. That's the camp with some tents in front of it. Participated in a sled haul race and drilled a lot of holes into the sea ice. Sea ice around Antarctica is frozen ocean water, and you have 2 plots here. The left-hand side shows the winter maximum for a specific year, with the orange outline being the 30-year climatological average. And the right-hand side here shows the winter minimum, again with the climatological average in orange around. You can see that this has not changed as much as it has in the Arctic, where you've seen a massive decrease. And you can also see that it changes massively between summer and winter. So this extent decreasing and increasing again every year of sea ice around Antarctica. That obviously influences the ocean and the continent itself quite significantly. And I'm going to talk you through this slide. It's quite busy. So on the left-hand side, we've got the continent, and on that, snow falls. That's fresh water. It compacts under its own weight and at some point forms ice. And this ice forms a very big glacier on the size of a continent and eventually it gets so heavy that it flows out towards the edges of the continent, and this thing is called an ice sheet. Once it reaches the ocean, it can float up and form an ice shelf. This is still fresh water. It's now just floating, and you've got an ocean cavity underneath. This ocean, if it gets cold enough, which is colder than about minus 1.9 degrees Celsius, can form sea ice. That is frozen ocean water. It is salty, but not quite as salty as the ocean. So when ocean water freezes, it rejects some of its salt in the form of brine, which is very salty water that sinks down and can form deep water and can also flow into the ice shelf cavity. This cold salty water is at the surface freezing point, but because the freezing point of seawater depends on pressure, and also this is salt water and the freezing point of fresh water is 0 degrees, which is a lot higher, you get melting of the ice shelf at depth. That adds fresh water to your already very cold water, making it more buoyant. It rises up, and this releases pressure from your water, and you can form supercooled water, so water that is still liquid but below its own freezing point temperature. At some point, this can form little ice crystals by snap freezing in the water column. You can think of that like snow, but under water, and then it slowly rises up because the ice is buoyant and can attach underneath existing ice. This is shown over here. So this is just a cross-section through the ice from the top with the snow atmosphere boundary to the bottom with the ocean boundary. Normally, sea ice will grow through heat loss to the atmosphere only, and it will form columnar ice where all of the crystals are very nicely aligned with each other. In places where we have supercooling, these little frazzle crystals that I talked about before, they grow larger, they attach to the underside of the sea ice, and at some point, the sea ice will grow into the interstices between these little crystals and form incorporated platelet ice. And you can thus tell how much of an ice core was grown through heat loss to the atmosphere versus how much was grown through heat loss to the ocean. To measure ocean properties, this is mainly described in terms of temperature, salinity, and pressure, and we cannot measure salinity directly. So conductivity is used to describe salinity, and then salinity is calculated from conductivity, temperature, and pressure. In practice, we don't actually measure conductivity, we measure the resistance of a cell. This is shown down here as a cross-section of this instrument. You pump water through it, it's got an electromagnetic field within it with 3 electrodes. You measure the voltage drop over these, you get the resistance of this entire setup, and then with some geometry, you can solve for the conductivity of the volume of water within the cell. Now, what happens if you've got particles in there that aren't conductive? That can be frazzle ice, it can be sand, it can be microplastic. You effectively reduce the volume of conductive liquid within that cell. And that is what I tried to describe in my experiments. To look at what this looks like in the field, if you put one of those temperature and conductivity sensors into supercooled water, ice crystals can form and block the intake of your instruments. And you get some extremely bad data, and I look oddly happy having that bad of data. So the freezing point temperature in water is calculated with this term here. Don't worry about the specifics about this, just that S is salinity, P is pressure, and A0 through A2 and B are constants. So it's reasonably easy to describe. In the open ocean, supercooling is generally on the order of about 10 millikelvin, so you need quite accurate sensors to resolve this. Large frazzle flocks, as you've seen on the previous slide, block the intake of the instrument, and that's immediately obvious. Your data is just terrible. Medium-sized crystals and flocks cause conductivity spikes. This is also quite obvious in your data. but small crystals cause a constant conductivity offset. This is not so obvious. We use supercooling to predict the presence of frazzle, and conductivity is measured to calculate the freezing point of water to know if something is supercooled or not. Frazzle in the water influences that conductivity measurement, and we're stuck in this cycle where we're not quite sure what is going on, and we only know that our data could be okay or it could not be okay. So I have this experiment set up over here where we have a temperature sensor, a conductivity sensor connected with ducting to a pump inside a bucket that is filled with seawater, and then a data readout at the top. I then added plastic particles in increments to that bucket. Why plastic particles? Because working with actual ice crystals, it's very hard to control your concentration of ice crystals, and also you're quite liable to damage your sensors by freezing them in. So these plastic particles are chosen to have material properties very similar to ice, so have a similar conductivity, have a similar size as small frazzle crystals, so they're 50 micrometers in diameter. They were chosen to be spherical, which frazzle is not, but it means that I don't have to worry about which orientation these crystals go through my sensor. And I had to add a surfactant, which is just laundry detergent, to my water to aid dispersion in there, because otherwise it clumps and floats. There have been some previous experiments not using plastic. Most of them use sand and mud, where the volume of particles was not well known. These studies all use the weight of sand and mud added instead of the volume of sand and mud added. The material properties of these particles are not well known, and not all of the studies use standard oceanographic instruments. So there are 3 that I could find. It's Maren and Pacour from 2017, who used standard oceanographic instrument, sand and mud in natural seawater. Held et al. Used natural sand and mud, but didn't use standard oceanographic instruments from Seabird Electronics. And Sun et al. Used sand and of different sizes and salt water made from sea salt, so not natural seawater. And they also do not use standard oceanographic instruments. This is what one of my experiment runs looks like. You have time on the x-axis and then different variables on the different y-axes. And each of these red lines is where I've added particles to my experiment. And you can see that the conductivity in the center here and also the salinity go down each time I add particles. So that's quite reassuring. It's doing what I think it's doing. And if you plot this up, you get a very nice linear relationship. This is change of salinity relative to your original salinity. So this shows a decrease in salinity with increasing particle volume. This is volume concentration in cubic meters per cubic meters of particles. And the red, pink, and blue dots are the results from my work, which was done at different salinities and different temperatures. And the orangey browny colors are results from Maren and Pacour. So we are within the spread of what they got for their results, but tend to have a stronger decrease in salinity per particle volume added. It's very nicely linear, what we see. And we can thus describe what we see as our measured salinity being equal to the original salinity of just the seawater plus our volume concentration of particles times a slope, which in this case would be negative. There's different ways of describing what happens in that cell theoretically. I tried a couple of them, and this is the only one that worked. I took this from a treatise on electricity and magnetism from James Clerk Maxwell, 1873. It's freely available on the internet, thanks to Google's book scanning efforts. And this section here just describes what happens if you have a conductive medium containing small spheres, which is exactly what I've got. And it has a relationship down here. Let's see this on the next page. It basically relates the measured resistance, which is just 1 over the conductivity, to the original resistance of the seawater, the resistance of the particles, Kp, and the volume concentration of the particles. Right-hand side again shows decrease in salinity with increasing particle concentrations. And now I've plotted all of my experiments, all of Helt and Men's experiments, plus a couple of theoretical considerations. So the yellow lines up here are the results from Le Men et al. The pink lines down here are the results from Helt et al. My results are the green ones, which fall right in the center of these two. And Maxwell's relationship is that bold green line going right through the middle of my experiment results. So that fits really well. The other things that I tried was just standard conservation of mass and salinity, which is the red line here, which doesn't really match my data at all. And you can fit Archie's law to this, but you need, which is the blue lines, but you need a negative formation factor, which makes no sense whatsoever physically. So now that we've got this linear relationship and know that it can be described by the relationship of Maxwell, what can we do with this? If you know your concentration of frazzle in the water, you can correct for salinity effects, but that needs concentration measurements of frazzle. This can be done with acoustic measurements, though that is difficult and quite imprecise. The Marsden Fund project, which partially funded this experiment, was awarded to Inga Smith as a PI to build, to design, build, and deploy HIPSME, which is a high-precision supercooling measuring instrument, which is basically a set of temperature conductivity sensors, as I showed before, which measure the ice-water mixture, then have a heating element, which melts the ice and heats the water. And then you've got another conductivity temperature measurement after that. And with the difference between the first and the second measurement, you can correct for the volume effects of ice melting and forming fresh water and calculate that into a concentration of ice that you had before, and then use that concentration salinity relationship to calculate the original concentration of frazzle and correct for supercooling. And also you can use the relationship that I presented if you're designing an instrument and you want to calculate how accurate it needs to be to resolve a given concentration. So HIPSME was deployed last year on board IceFin. This slide over here shows Inga Smith, the PI, and the AI is Brittany Schmidt, Lars Smedsrud, and Greg Leonard, with IceFin, which is a remotely operated underwater vehicle, which has a modular science bay over here. It's got a water intake at the front where we would be pumping the water into HIPSME. And you can see that if you deploy anything into supercooled water, you get ice formation on absolutely any rough surface that you've got. There we go. This is the part of the HIPSME design team with Dan and Pete, and it was also designed by Matt Meister. And this is HIPSME itself. It can go into IceFin or it can be deployed on its own. So that's the end of the particles in water part of the talk. Now I'm going to switch scales and go from liquid water with a little bit of ice into it into ice with a little bit of water in it, and talk about the interannual variability of fast ice thickness in McMurdo Sound. So very obviously, some years ice is thicker, some years ice is thinner. And this is influenced by heat loss to the atmosphere, which is in turn influenced by air temperature and wind speed, and the date of fast ice formation. So if it had more time to grow, it will be thicker. The date of fast ice formation in turn is influenced by air and ocean temperature and the storminess, as southerly storms in McMurdo Sound can blow the ice out of the sound and thus delay fast ice formation. And also heat loss to the ocean influences sea ice thickness, and that's regulated by ocean temperature, salinity, and currents. This is McMurdo Sound within Antarctica, the red dot over here. So we are on the western side of the Ross Ice Shelf. We've got Ross Island to the east and the Victoria Land coast to the west, and to the south there is McMurdo Ice Shelf, and then Ross Ice Shelf is over here. I'm using meteorological observations from 3 observatories. One is Marble Point on the Victoria Land coast, and the other 2 are Scott Base and McMurdo Station. We've had wintertime observations of sea ice thickness at the cyan locations shown here on the ice for different years. And also I used manual observations of sea ice thickness at the United States sea ice runway, which was around this spot here at the 2017 probe location. This was roughly where the sea ice runway was. A note on fast ice versus pack ice. Fast ice is frozen ocean water sea ice, which is attached to the land, an ice shelf, or grounded icebergs, and stays in place. So it doesn't move around. And that's just shown in the blued out area over here. Pack ice is probably what you're more used to thinking about. There's this large and small bits of ice which float around on the ocean, moved by wind and currents. And an ice shelf is a floating glacier, which is way thicker than fast ice is. So our long-term observations in McMurdo Sound started in 1996, and on all of these orange years through the timeline until 2020, sea ice mass balance station has been deployed here. This has a snow sensor, data logger, and then a thermistor string, which goes through the sea ice and into the ocean, and measures temperature at predefined depth intervals. From that, you can tell when a thermistor freezes in and calculate the thickness of the ice from the temperature. What you can also do is do manual measurements, and you can see this over here. You drill a hole through the sea ice, and we've got the ice on the top and the ocean underneath here. You pull your drill bit out again, and you lower a tape measure through, which has got a weight at the bottom with a crossbar, and you pull that up, and the first time it catches, that is the depth of the attached platelet crystals at the bottom, and then you keep pulling up a little bit. And we can see this here, it takes a couple of tries, and when you can't pull it up any higher, here, that's the depth of your consolidated sea ice thickness, and that is what we are also measuring with the probe. To get thickness from temperature, as I already said, you can use the difference between ice temperature and ocean temperature. So the top plot here shows temperature with depth and time, and the ice is colder at the surface, gets warmer the closer you get to the ocean, and the ocean is isothermal at its own freezing point. And all of these dots along here are manual measurements of sea ice thickness and the thicknesses that we got from the temperature, and this lines up reasonably well with what you can already see, that it changes temperature at around this depth. You can also look at the vertical gradient of the temperature, and again that changes quite abruptly along this line here. So that is consolidated sea ice thickness. To get the component of ocean heat flux, we don't really have measurements for this, so we approximate this by looking at the depth in the ice core, where we switched from columnar ice growth to the incorporated platelet ice. You can see this in ice cores, so this is just a piece of sea ice from the surface to the ocean, and looked at under cross-polarized light. You can see the columnar ice is very nicely aligned with itself, and then over here once you get to that transition between columnar to platelet ice, it gets really higgledy-piggledy. So it's reasonably easy to see that. To study interannual variability at a location, you obviously need a long time series, and McMurdo Sound is quite unique for that. It's over here, and earliest observations of fast ice thickness and subice platelet layer thickness were done in 1902, and it has not really changed much since then. There's been some studies looking at the fast ice extent and breakup and its correlation with winter storminess in this area. But most of the studies of ice around Antarctica focus on pack ice and look at the sea ice extent, since that is something that you can measure from space with satellites, whereas thickness is not something that you can measure with satellites yet. Other locations where there's fast ice data is Davy Station, Lutzow Bay, Atka Bay, and the South Orkney Islands. And the state of the ice there has been correlated to sundry variables, both atmospheric variables as in temperature, pressure, and wind speed, but also climate patterns, which are SAM, ENSO, tropical sea surface temperature, and so on. So what is one of these climate patterns? I'm going to talk about two of them because those showed most correlation with my data. One of them is ENSO, that's short for El Nino Southern Oscillation. That is what you would normally know as a seesaw in ocean temperature and atmospheric currents over the equator in the Pacific. But this can also influence pressure patterns throughout the world. And one of the ways this influences Antarctica is that during El Nino years, which is just one phase that the seesaw can be in, you've got higher pressure over the Amundsen Sea. And I have to think about what happens on southern hemispheres. Okay, so higher pressure, this circulates counterclockwise, and you will have warmer air being pushed towards the Ross Sea and have less sea ice here, and colder air and more sea ice over the West Antarctic Peninsula. And during La Nina years, you've got exactly the opposite pattern. And so seesaws between these two states on sort of the 5 to 11 year cycle. It's not quite periodic. The southern annular mode, or SAM, also switches between positive and negative phases. And again, this is linked to air pressure around Antarctica. It influences the strength of the vortex around Antarctica, which is just this band of really strong winds. And during a positive SAM, you've got cold winds and more sea ice in the Ross Sea. And during a negative SAM, you've got warm winds and less sea ice in the Ross Sea. So what does all of this look like if we plot it as a timeline? The top panel here shows monthly mean sea ice thickness anomaly versus time from 1985 to 2020. And I've chosen 4 months for which to look at sea ice thickness: August, September, October, and November. The filled circles are the ones from our sea ice mass balance station, and the open circles is manual data from the sea ice runway, which was reported on in Kim et al. In 2018. The grayed out area here is a time period during which large icebergs were parked at the mouth of McMurdo Sound and influences the fast ice in the sound. So I'm taking out all of the multi-year ice measurements we've had in that time period because they're just not representative. The next panel down shows mean annual freezing degree day anomaly. That's just an integral of how cold it is versus time. And the mean annual air temperature anomaly. And as you would expect, they're nicely anti-correlated to each other. The next one down shows mean annual wind speed anomaly, with in black the total wind speed, in blue the U component of the wind speed, that's the meridional component, sorry, the zonal component, or how much does the wind come from the east, and the V wind component, which is the meridional component, how much wind comes from the south. And the bottom panel then shows normalized indices for southern annular mode, El Nino Southern Oscillation, Atlantic multidecadal oscillation and the tripole index of the interdecadal Pacific oscillation. And these all wobble along, and just looking at it, you can't really see much of a correlation between any of these annual averages and sea ice thickness. So what I did is that I calculated lagged monthly correlations and seasonal correlations for all combinations of atmospheric drivers, climate patterns, and months of sea ice thickness observations. And just looked at linear regressions of these. So that's reasonably simple. You've got thickness over here, and for example, the March, April, May average of air temperature at Scotch base, and then all of the different dots, colors are different years. And I'm sorry, I think in sea ice increasing downwards, so this axis is flipped to what you would normally think about. But this shows that if you've got colder air temperatures, you've got thicker ice, which is what we would expect. This is described by the R-squared value, which is the correlation coefficient, which just shows how much of a percentage of the variability in this data is explained by that straight line. And the p-value just shows how likely is it that our line is actually perfectly horizontal, and we just happen to have found one that slopes through it. So the smaller the p-value is, the more likely it is that this is a true correlation. So I'm only looking at correlations where the p-value is smaller than 0.05, so where there is the chance that I'm making an error here is less than 5%. And I'm only looking at R-squared values larger than 0.2, so only things where more than 20% of variability is explained by my regression. This one here on the left, if I were to just take a ruler and draw a line through it, I'd probably draw a line through it as it was drawn here by my plotting program. But I also get things like here on the right-hand side, which the R-squared value is 0.47, the p-value is lower than 0.05. But if I exclude like just 2 data points, as in these 2 outliers here, that could be a horizontal line, it could not. So not always is a mathematically significant correlation easily visible on a plot. So I'm going to exclude these manually later on. I'm going to show these in forms of heat maps, and I'm going to walk you through just an example and then show you what my data looks like. So on the left-hand side, there will be a table which just describes the combination of variables which I have used. And then my data is split into 3 time periods. One is just using all of the data that I have from 1986 to 2020. The next one is just using the manual measurements from the sea ice runway from 1986 to 2013. And the next one is just using the automated measurements at the sea ice mass balance station from 1996 to 2020. All of these have 3 columns. The first one shows the slope of the correlation. If that is shaded green, it's anti-correlated, and if it's shaded brown, it's correlated. And the next one is the R-squared value, and the next one is the p-value. And if these are more cyan, the regression is lower and less significant. And if they're more pink, the correlation is higher and more significant. And if it's black, there is no correlation. So just to recap, air temperature's effect on sea ice growth. If we've got colder air, there's more heat loss to the atmosphere. We've got thicker ice, and vice versa for warmer air. And this is happily what we do also see in our data. So this shows all of the correlations that I found with air temperature, and they are all anti-correlated, so they're all green, apart from this one, which I honestly don't quite understand, but ignore for now. There weren't any correlations with freezing degree day or with temperature over the data that was presented in Kim et al., which does also match the analysis that they did in their own paper. So that's a nice sanity check. We get the same result. And most of the anti-correlation that I see here is for months between March and August, which is the main growth season of the sea ice in the Sound, which again also makes sense. If it's colder, the ice is thicker. The next thing that I'm going to present on is the effect of winds and storms on sea ice thickness. And for that, we've got to talk you through what winds in McMurdo Sound actually look like. So this is a plot that I took from Greg Leonard's paper in 2020 on the anomalous winter sea ice condition in 2019. And these show wind roses. So where does wind come from? And the left-hand side over here shows all data, and the right-hand side shows just the strongest winds. And you can see that if you look at all of the data, most of the wind comes from the northeast. Actually, so much wind comes from the northeast that this is cut off, because otherwise this box would go like all the way up here. If you look at the strongest winds only, though, those come from the southwest. So it does matter which direction does the wind come from in McMurdo Sound. Looking at just heat loss, higher wind speeds will mean more heat loss to the atmosphere and thus thicker ice. Lower wind speeds, the opposites. If we look at just directions, strong northerly wind will push ice into the Sound and cause an earlier fast ice formation and thus thicker ice. Strong winds from the south will blow all of that ice out of the Sound, which you can see over here with the open ocean forming with these wind streaks where you can see where the wind is coming from off the ice shelves, and that will cause a later fast ice formation and thus thinner ice. But also northerly wind is generally warmer than southerly wind, apart from in winter where very strong southerly wind is actually warmer. So this is a bit complicated, and that is also seen in the correlations that I see here. Please ignore the middle one that didn't quite have enough data points for the modified storm index, which I'm presenting here, to be significant, so ignore. For the other years, most of it is anti-correlated, meaning that if we have less storms coming through, our sea ice is thicker, which we would expect because it can form earlier, with the exception of April storminess and late season storminess over here. And I'm going to have to think a bit about what that exactly means. If we look at just wind components, so not just southerly storms, but using all of the wind data that we have, we can look at the southerly wind component, that's the V component of wind, and that is correlated with sea ice thickness. So these values are all shaded in brown, that will positive, meaning that stronger southerly wind causes thicker sea ice, which makes sense if your wind isn't so strong that it blows out all of your sea ice, but your wind is still cold and from the south and can thus increase heat transport to the atmosphere. If we look at the overall wind, that is anti-correlated with our sea ice thickness over most of our time periods. So that means that the windier it is in general, the thinner the ice is. This can be a factor of that this obviously measures all of that northerly wind as well, and that can be warmer. But again, this needs closer investigation, what exactly is happening here. I tried to look a bit at the ocean component, but again, I don't have continuous ocean observations over my sea ice thickness observations. But what was highly correlated was the November sea ice thickness, so late season sea ice thickness, with the depth of the platelet ice transition in the sea ice. And that means that if you have more columnar ice, your ice in general is thicker. So if your ice has had a chance to grow thicker before your ocean supercooling sets in later in the year and starts forming sea ice, then you have thicker ice. there weren't any convincing correlations between the depth of that plated ice transition and a polynya proxy. Gemma Brett published a paper a couple of years ago looking at a proxy for the opening of the Ross Sea polynya and correlated that to the thickness of the sublice platelet layer in McMurdo Sound, which is why I was looking at this in any case, but we do not see any correlation. And we don't see any correlation between the date that the fast ice forms, so the freeze-in date, and the storminess itself. So that kind of argues against that the correlation we see with storminess and sea ice thickness is through the pathway of when does this ice form. Unfortunately, I don't have that much information of when ice forms, so this might be a sampling bias that I have here so that I can't see a correlation. There's some signs of possible preconditioning in the ocean, because we do see correlations with summertime southern annular mode, ENSO, southerly wind speed, and overall wind speed, and that also merits some further investigation. Some things to keep in mind when thinking about this is that the time series that I studied is only just over 30 years long, which is the minimum length for climatological averages as defined by the WMO. The location of our measurements changes from year to year, so we are introducing a spatial component. I did try to check for this by calculating correlations between location in sound and thickness, and I didn't find anything, but that doesn't mean that there isn't any component there. The effect of large icebergs in McMurdo Sound in the middle of our observation period is likely quite strong. And we have no long-term observations of the oceanographic conditions during our study period. So 1986 until 2020, that data year-round just does not exist. And we can thus not look at this really important driver for fast ice growth in the Sound. Similar for freeze-in data, as I said before, there just doesn't exist data from satellites at a high enough resolution to look at when did this ice form for all of those years. So in conclusion, there were no trends in thickness over time, so the ice isn't getting thicker or thinner in McMurdo Sound. The highest correlations that we could see were with freezing degree day, air temperature, and southerly wind, as you would expect. There's no significant correlation between the proxy for polynya opening and fast ice thickness. There's some indication of possible preconditioning in the ocean, which merits further investigation. And there's an urgent need for better and continuous observations of the fast ice advance and retreat in McMurdo Sound, as well as year-round ocean observations to understand the system better. Future steps would be to investigate forcing mechanisms more closely, especially for the wind forcing and for the climatological patterns that I investigated, and then possibly look in more detail at the ocean component through modeling or reanalysis. If you know of any studies looking at this kind of data, please let me know. I'm always happy to look at what other people did there and learn from it. And if you have any questions, now is the time to ask. Thank you very much.